Hello, everyone. I'm Francesco Cameli, and I'm going to be talking about Omni, which is a domain-specific language that I've been developing for the past 9 months, and it's going to be part of my submission for my master's thesis at the University of Huddersfield. About me, well, I'm mainly a composer and improviser. I'm not an engineer at first, at least. I'm self-taught, so I've got no formal computer science background. So everything I've done is basically like out of my own interest and out of my own needs as a composer and improviser. Uh, what is Omni though? So it's a domain specific language for developing audio algorithms. And its scope is to be as minimal to use as possible while being cross-platform and cross-application, which means that you would write your Omni code once, and then you would expect that to be deployed, everywhere. In this case, everywhere that you've written a wrapper for, but more on wrappers later. There are similar projects out there. The most notable ones I would say would be Gen in Max, which is a proprietary language inside of Max MSP, which allows you to still do low-level DSP. It's very easy to prototype code with it, and it exports to C code. But my main problem with it is that it has fixed data structures. By that I mean that the individual objects that you have are given to you, and that's that's the lower level you can get into. Another language out there would be Faust, which is developed by Graham in Lyon. It's a functional programming language, which is, as Omni, it's open source and it's cross-platform. But my main problems with it would be, well, the functional approach, which I don't personally enjoy that much, and also the monolithic approach that he has to exporting stuff. So the Faust executable can export code to a plethora of things, but those things are all embedded in the same executable, while my approach would be more of having a more minimal executable, and then you would write wrappers around that to export to different things, and more on that later again. So why did I develop Omni? Well, as I said, I wasn't satisfied enough with the current tools out there. And also, but at the same time, I'm not skilled enough to write up my language from the ground up in terms of writing my own parser, lexer, compiler, etc., etc. Maybe do some LLVM stuff. I mean, I looked into it, but I realized quite soon that it would take me much more time. So what's the solution for me? Well, the solution for me is a thing called metaprogramming, which is basically something that allows you to write code that produces other code. And that's the code that's going to be compiled. And in my case, the language I'm using to develop this Omni language is Nim, which has amazing metaprogramming capabilities. So the whole Omni language is actually developed in Nim macros in this case, which are the core of Nim's metaprogramming. What does Omni look like though? Well, something like this. It's basically based around a scoped syntax where each individual scope, which is determined by a keyword and then a colon, has a different purpose. So it's kind of, let's say, I wanted to get it to do the most minimal thing. So just the DSP part without having any overhead. So this is a language that's just for the DSP or the low level algorithms. So it allows you to have custom data structures, and as I'm going to show, and it's guaranteed to be memory safe because all memory allocation all happens in something called the init block, which I'm going to be explaining later again. So the first two blocks will be the ins and outs block, which allow you to define your number of inputs and outputs, names for those, and for example, default, minimum, and maximum values for those. The next block will be the init block, which is where all the memory allocation will happen if you're declaring your own data structures that you want to use. In this case, in this example, we're simply going to declare a variable called delay, and it will be of type delay, which is an inbuilt struct, and that's going to be allocating memory of delay length in terms of length of samples for a delay line, for example. Then inside of the init block, there's another thing called the build block, which allows you to pass on specific variables that you allocate in the init block through to the perform and sample blocks, which are the ones that actually do the DSP processing. So the perform block happens at the block level, while the sample block happens sample by sample. So after going very fast about that, we're going to do a live demo about it. So how would you install Omni. So if you have Nim installed, I'm using the Nimble package manager. So you just go Nimble install Omni. And that's it. You would have Omni installed. Now you would have the Omni compiler executable. And let's do some Omni code perhaps. So I've got some examples here. So if anyone wants to interrupt me at any point for any questions, just feel free to do it. So this is a very simple example of a sine wave, for example. So as you can see, well, I've also developed this VS Code syntax highlighting just to make things a little bit clearer. I'm using VS Code as my text editor. So here, for example, we just declaring one input, which with the name frec, and our default will be 440. And let's say that our oscillator would go from 1 hertz to 20,000. And this is where we would express that. Then we just want to have one output, which is the actual oscillator. So in the init block, we're declaring a variable called phase, which means that this variable will be kept alive. So we can, for example, increment the values on that, store stuff on it. And that's what we're doing for an oscillator here. We're actually calculating, for example, the frequency increment with the first input divided by the sample rate of the system. Then we're just saying, okay, we want the sine of that times 2 pi at the output. And then we're just updating the counter. So if we want to compile that, we would just call omni and then omnisine.omni. Sorry. And what we get back is actually a share library and the header file. So the header file contains all the entry points for that share library. The most notable ones will be the init global or init alloc, which allows you to, if you're writing a wrapper around Omni, around this shared library that you generated, to define your own, for example, allocators or your own print function so that it can be embedded anywhere. The other, of course, important parts are the initialization, which take care of initializing the bit of memory, and the perform, which is actually doing the DSP loop. So to hear what we created, what we coded, I'm going to use the omnicollider wrapper, which is a wrapper around Omni that generates SuperCollider unit generators, because that's what I mainly use. And I would just call omnicollider. So this is a separate executable though, because my idea for Omni is that the Omni compiler will be very minimal. We'll just compile shared or static libraries, and then you would write wrapper around this procedure to create your own wrappers for whatever projects you have. So it means that I don't have to maintain, for example, if you want to develop an Omni wrapper for open frameworks, for example, which I don't use, I wouldn't have to maintain it, or pure data or whatever, or a BST wrapper. That this allows me both to code it myself if I need it, but also having someone else doing the job instead of having a plethora of like pull requests and having to maintain a huge code base, which I wouldn't use personally, because the first thing for me for Omni is that I wanted to use it to create my own algorithms. So enough about that. So we created this omnisine unit generators. So if you go to SuperCollider, for example, we have the omnisine here. And as we can see, we have the default value of 440. If we want to play that out to our speakers. So I just want to, I'm going to start super low with volume because I don't know. Can you hear it?
Yep.
Yeah, okay. So yeah, as we can see, we created a simple sine wave oscillator, which is not that exciting to be honest, but it's just to show the like sort of the hello world of the audio realm in a way. So onto a little bit more complex example, we're introducing structs now. So a struct is a way for a code for a programmer to define its own data structures. For example, we're defining a struct called phasor here, and a def, which is a function in Omni, which is actually going to use another inbuilt struct, which is called data. So data allows you to have an array of anything inside of Omni. So in this case, we're declaring an array of phasors, type phasor of the number that we input, for example, in the init block in this case. And then we're initializing those phasors, and we're just returning the array. So in the init block, we're just getting the number of sine waves that we want to generate from the user. we're calculating, for example, a scaling of the amplitude. So this is calculated the first time you create the object, not every sample. And then we're creating those phasor by simply calling the depth. In the sample block, we're just looping through the array of phasors, updating the phase coefficients according to like a multiplication of the frequency. So we're generating like sort of a bank of sine waves with equal amplitudes. So if we compile this, sines.omni, when we go into SuperCollider, omni sines. So for example, we can have, if we have just one sine wave as before, we're just gonna have the same, let me just turn the volume down again, the same sine wave as before. But in this case, for example, by simply adding to the code this data structure, which allows you to have an array of anything, in this case, an array of a struct phasor, this allows us to have a bank of sine waves just like this. So if we want 10, if we want 100, well, it's going to clip because it's all calculated like we're calculating sine. We're not taking like a sine table to save memory cycles, but just to show you that, okay, we have 10 sines, and it's as easy as that to just code it. Again, this is all coded in the same Omni file, for example. What if we want to split up our code into more reusable bits of code? Well, in this case, we're introducing something called require, which is sort of like an import statement in Python. So we split our file into omnisines2.omni and phasors.omni. So phasors.omni has two struct in this case. So the struct phasor that we had before, and then a struct phasors, which is storing the number of phasors, the amplitude, and the data of phasors, so the array of phasors. And we have the same function here in initializing it. So we're simply requiring this bit of code here, and we're just using it to initialize, and then we're going to use this. So we pretty much abstracted out the core of our algorithm to another file that we're going to reuse, perhaps not just in this project, but in whatever project. It's just an easy way of you to structure your DSP code. And the results will be the same. Again, we can even abstract even more. For example, in Omni Sines 3.omni, we actually have just 13 lines of code. We are just declaring number of inputs and outputs and simply calling an initialization function and a process function. And these ones are sines.omni file, which is requiring the phasors that we had before, and we're just adding a process that's just abstracting out the calculation of the sine waves in this case. And for example, if we compile this, and we go to SuperCollider, we're going to have the same result, but we have more bits of reusable code that are easier to maintain. A little bit more of an interesting example would be to using the same bit of code, but having the amplitude scaled, for example, by the inverse. So we generate sort of a bank of sine waves that will generate a sawtooth in a way. We're just generating the harmonics with the decreasing amplitude. So if you see here, the code is actually the same, the code we're actually compiling, because we're still calling the init phasors and still calling a process function. But this time we're importing it from another file, which is called sines2saw, which is pretty much the same as the one we had before here. It's just that the amplitudes are scaled by the invert, like they're just scaled by the count of the number of sine waves, so that we have the harmonics being generated. So we compile this sines to omni sines to saw, and we go to SuperCollider again. This time we're going to have an approximation of a sawtooth wave according to number of harmonics we gave to it. Of course, the more harmonics we give it, the more precise we're going to have it. Of course, this is not the way you would generate a sawtooth wave, but it's just to show how flexible is the Omni language in terms of like declaring bits of reusable code DSP code that would look as simple as possible, as minimal as possible, and I think are quite elegant in a way. But that, I mean, of course, I'm biased because it's my project, I guess. So future work regarding the language. So there's a lot of work, of course. It's still a very young project. The main thing for me would be to develop some sort of hot code reloading or JIT compiler for the Omni language, so that sort of like Gen, you would just have this sort of this object or whatever you want to call it that can recompile Omni code as you code it. Another interesting thing would be WASM compilation, so using Omni code on the web. Of course, Omni test to test algorithms on the fly. It's directly linked to having hot code reloading or JIT compiler working. Then oversampling embedded directly in the language, FFTs support, and other things like this. But of course, these are still future work that's going to happen at some point, but it's not there yet, of course. So I hope I gave a rough introduction to the language. Of course, there's a lot to talk about. If you're interested in this, you can take a look at the website, which is right here, at this link right here, which is a very simple website that just shows a little bit of documentation about all the different parts that I don't have the time to look into, but for example, stuff about the syntax, why things are like this, how you like the best practice to declare variables, a reasoning why I don't use let or var statements and stuff like that, and all sorts of other things that there's no time to look into. The repository, on the other hand, is on GitHub at this link, so feel free to check it out and fork it, use it, download it, and I guess that would be it for me. Other questions?
Great. Thank you very much, Francesco, for your presentation. While we're waiting for other questions to come in, I had a question. Do you have any way of handling time domain types of situations, so things like delays,
Yeah,
sequencing?
So there's an inbuilt delay. Let me go to the website. There's an inbuilt delay class in the standard library. You would just declare it as you just declare it in your init block, and that would just take care of initializing it. And then you can call some sort of functions that are developed for you, like a read function and a write function. It's taking care of like cubic interpolation, all the sort of things that you want to do with a delay line. You just have to tell in the sample block, sample by sample, like what you have to write in the delay line, what you have to read out, and that's it.
Great. And how long have you been working on this for?
Like 8 to 9 months, something like that.
Wow, amazing. And where did the original inspiration for this come from? Did you feel that?
Yeah. No, it's interesting because at first last year, I graduated with a project called Julia Collider, which embedded. I don't know if you know about the Julia programming language. It basically embedded the Julia runtime inside of SuperCollider, so that you would call the JIT compiler of Julia while using SuperCollider memory. It was kind of this kind of bloated project, but it will allow you to write your Julia scripts and use them as SuperCollider unit generators. Mm-hmm. So that's where my interest first come of developing my own language, or sort of my own syntax. I wouldn't call this a proper language. It's more of a DSL, very specific, because I'm scared to call it a language because it's all developed via metaprogramming. So it's not a proper language per se. It's more like a dialect in a way of the Nim programming language.
But I guess the Nim programming language itself is also kind of a new trend, right? So I know an embedded audio developer who is also very excited about Nim, and maybe I can convince him to do a talk about Nim at some point at this meetup. I very much hope so.
I mean, Nim is a very fascinating language to me. Of course, I don't come from any bias background, since I'm self-taught. I haven't worked. I worked 6 months at IRCAM and 6 months at GRM in Paris as my placement year 3 years ago. But I'm not like an experienced developer biased by other languages, let's say. So I just found out about this language. It was quick enough. It was fast enough, and it would leverage on other strength, like for example, it compiles them to C code, and then you can use whatever C compiler to that. So that's, to me, that's a big plus, because I don't have to maintain, for example, a Bella board support, because that comes already, because the Bella board has a GCC compiler, so I don't have to maintain that. But
So
this
do I
compiles
understand
everywhere
it?
that C
Yeah.
compiles to, in a way.
So do I understand it correctly that you basically it's basically a meta language on top of Nim, and then
Yeah.
Nim itself is a new programming language which compiles down to C.
Yeah, exactly. Well,
So it's
Nim
this
can
kind of
compile down
layered.
to C or JavaScript, so it's actually easy to do web stuff as well. But if you, of course, you want speed. Nim itself is a garbage collector language, but in my case, I'm using it without any garbage collector. Like, you have the option of turning the garbage collector off, and I'm handling my own memory in this case, of course, because it's quite sensible for real-time audio to know when you're allocating memory, when you're freeing memory, and you know, make sure that that doesn't ever happen in your DSP loop, etc., etc. But Nim allows you to do all this sort of things. So Omni sort of generates Nim code under the hood, and that Nim code generates C code under the hood, and that C code is compiled with a C compiler. That's the road that the Omni code takes down to being compiled.
That's quite an interesting stack that you have going on there. It's yeah.
I have a. I'm not sure if that's my dog barking or somebody else's.
I think it's here. Yeah, apologies. So I'm here in Greece and I just arrived here today. So I don't really like, I'm kind of outdoors, and there's like neighbors and dogs and cats, and there was like people drilling something behind me earlier. So it's a bit unpredictable what's going on. I'm gonna try to mute my mic when I'm not speaking. Maybe that's gonna help.
Okay.
So it's a bit today it's a bit unpredictable meetup.
That's okay. Okay, we have a few questions from people. So Sid asks, "What is Nim?"
That's a good question. It's a programming language. It's a new programming language. Well, not so new. I think it's like 9 years old now or something like that. But it's getting attention, I guess, just lately. So it's a programming language. It's a systems programming language. So you would just use it as a drop-in replacement for something like C, C++, or Rust, which has amazing metaprogramming capabilities. So metaprogramming allows you to write code that generates other code.
Okay.
In a way. That's the most simple definition I can come up with in a second.
Okay. We have another question from Sean Laptiste, who asks, "What is the most complicated processor that you have created with Omni?"
That's interesting. Well, I've coded a Forces. I don't know if anyone knows that. It's a Eurorack module.
Nice.
Which I think there is somewhere an example in Gen. So I just copied that stuff out and coded in Omni. That was quite a complex one. I've developed some reverbs, artificial reverbs, some feedback delay networks, some filters, but those are kind of simple, like, in a way, like yeah,
Very cool.
oscillate, like anti-alias oscillators. I don't know.
Okay, great. And there's a question from Staging, I think. I hope I pronounced that correctly. So, and he says, so this transpiles to C or C++, or does it also compile that code, i.e. using LLVM to binary directly?
No, it just so I don't handle myself the G transpilation, the C transpilation. That's something that Nim does. So I generate, Omni generates Nim code, then Nim code generates C code, and the C code gets compiled with whatever compiler you want to use for compiling that C code. So it's not like if you want to use the C-Lang compiler, it's not using the LVM intermediate representation at any stage. It will be interesting to look into that. There's actually some Nim bindings for that, but I haven't had the time to look into those.
Okay. And I imagine the answer to this would be no, but can you have an external MIDI device's input?
No. So Omni just takes care of the DSP. So I wanted to have something extremely minimal that just does that one thing, and then you would, use that. It just takes care of doing the DSP. Then how you would interface with that it's another topic, I guess.
Great. Okay. That appears to be all of the questions. Thank you very much, Francesco.
No,
Pardon me.
thank you very much to you.
Yes.
It's been fun.
Thank you.